Welcome to our mix for ATN 1.4 in the chips using a chip model. Our next lesson, we're going to focus on the learning target, how can you use a chip model to represent addition and subtraction? So where does this idea of a chip model come from? Well, when business records were kept by hand, accountants used red ink for expenses and black ink for income. If your income was greater than your expenses, you were in the black. If your expenses were greater than your income, you were in the red. You wanted to be in the black. So let's look at a problem, and then we'll think about how the red and black concept comes back. Julia has this problem to solve. Tate owes his sister $6 for helping him cut the lawn. He earns $4 delivering papers. Is Tate in the red or in the black? To solve this problem, Julia uses red and black chips to model income and expenses. Each black chip represents $1 of income. Each red chip represents negative $1 of income. In other words, an expense. So let's take a look at what she created for a chipboard. Here's what she represents for the situation. You can see here a total of 6 red chips that represent the negative $6. In other words, the $6 that Tate owes his sister for helping him cut the lawn. You can also see the black chips, which are $4 total, which is what he brings in from delivering papers. So how do we decide if he's in the red or in the black? Julia decides that Tate is in the red $2, or has negative $2, and she writes this number sentence, negative 6 plus positive 4 equals negative 2. However, why do you think that Julia concludes that negative 6 plus positive 4 equals negative 2, based on the chipboard? You might have started to think about how a negative and a positive, if they're combined together, will create something that we can call a zero pair. In other words, they have a value of 0. So looking at that board right there, if we were to line these up, sometimes it makes it a little easier to see that way. We have a total of 6 negative chips, right? 6 red chips. And we have 4 positive chips, also known as black chips. If I go ahead and cancel out all of those zeros, I'll notice that I'm left with 2 negative chips, which means that even though the board itself has 6 red chips or 6 negative chips and 4 black chips or 4 positive chips, the overall value when the zeros are taken into account is negative 2. So what would be another way to show negative 2 on the chipboard? Well, for example, I could just include 2 negative chips. That would have a value of negative 2. What if I had 3 negative chips? If I want to make that a value of negative 2, I'm going to need 1 positive chip, which will create 1 zero pair, and then leave me with an overall value of negative 2. What if I had 4 negative chips? If I want a value of negative 2, I'm going to need 2 positive chips, again, to cancel out and create some zero pairs, and thereby leave me with a value of negative 2. Again, it's important to know that those chips are still there. It's just the overall value of the chips on the board is negative 2. So now what are some ways to show a total value of 0? Just thinking about a chipboard in general. For example, I could have 2 positives and 2 negatives. Those would simply create 2 zero pairs and cancel out, leaving a value of 0. I could have 4 negatives. I would need 4 positives to cancel out all of those chips. for a total value of 0. Again, the board itself still has those chips on it, it's just that their overall value is 0. So you might be noticing that if I have the same number of positives and negatives, I have a value of 0. So now Julia changes the board by adding 1 red chip and 1 black chip. By how much has she changed the total value? So if I add in 1 black chip up here at the top and 1 red chip also at the top, I can see that I now have a total of 1, 2, 3, 4, 5, 6, 7 red or negative chips, and I have 1, 2, 3, 4, 5 positive chips. When I cancel out the 0 pairs, I see that I'm still left with a value of -2. So in other words, by adding 1 positive and 1 negative, I simply added 0 to the original, and I didn't change the value at all. Lastly, what groups of red and black chips can you add to the board that will not change the total value on the board? Well, this is the concept we've just been talking about. If we add 0 to the board, we don't change the value. So as long as I add the same number of positives and negatives, so in other words, if I add 3 positive chips and then I add 3 negative chips, I won't be changing the overall value of the board. I'm simply adding 0 each time. And again, if you imagine -2 plus 0 plus 0, right, as long as I keep adding zeros, I'm still going to get -2. Now we're going to talk about some strategies you might want to keep in mind as you're working with your group tomorrow. For example, on problem A, you're asked to use this particular chipboard as the starting value for each part. It might take a little bit of time to draw out all of those pieces, but it's going to be important tomorrow. So you might want to use colored pencils. You also can use what are called plus or minus pieces. So if you just like to draw little plus or minus symbols, that might be a little easier for you. So for example, when it comes to the original chipboard, I could show that it has 8 positive pieces, and I can show that it has 12 negative pieces. And you'll notice that I'm lining up the positive and the negative pieces so that it's really easy then to see when I make a 0. So one of the strategies I would encourage you to use tomorrow is really drawing careful, clear diagrams so that you can see what's happening in the situation and really clearly know when a 0 is made. Another problem you're going to see tomorrow is problem D, where you need to fill in a table. And it takes a little bit of practice to look at this and kind of make sense of it. So for example, on number 1 here, you can see that you're starting with 3 red chips. 1, 2, 3. And so that's a value of -3 that you're starting with. That's the first part of your number sentence. I'm going to just sketch those 3 red dots. I'm just going to write 3 minus signs here. And then the rule, that's kind of like the change from our temperature problem, we're going to add 5 positives. And so I'm going to write those in over here. 1, 2, 3, 4, 5. I'm also going to write that into my number sentence, plus 5 positive. And then I'm going to think about what I'm going to end with. And so again, this is where my zeros come into play. I'm going to look for any combinations of a positive and a negative that can combine to create a 0. And now I can see the value that I'm left with. I'm left with 2 positives. And so you can see here you're going to go ahead and fill in 2 black dots for 2 positives. And my number sentence is going to say 2. If you connect this back to your number line problem from yesterday, you could think about how if I'm at -3 and I add +5, I'm going to get to +2. Again, you're not being asked to do that right now, but you might be starting to think about connections between the different models that you've seen. Another type of problem you're going to see is E. Describe a chipboard display that matches each number sentence. Find the missing value in each case. So for example, on number 1, I have 3 positives as my starting value. And I have a subtraction sign here, which subtract is just going to mean to remove chips. So it's asking me to remove, and I need to really pay attention to if it's asking me to remove positive pieces or negative pieces, because it makes a big difference. I'm being asked to remove 2 positive pieces. And I have 2 positive pieces here. I can just draw a circle around them and show I'm moving them away. And then I can clearly see I have 1 positive left. However, what if the problem had said 3 minus negative 2? You might have thought to yourself that if I had 3 positives, I can't take away 2 negatives. Or can I? Well, if I add 0 pairs, right? Remember, adding a positive and a negative is the same as adding a value of 0. It doesn't change the overall value. However, if I add 2 0 pairs, I now have 2 negatives that I could take away. So if I was doing the problem 3 minus negative 2, the answer would be positive 5. Think about another one here. What if I had 3 minus positive 7? Again, I have 3 positives, but that's not enough if I want to take away 7 positives. So I would need to add more 0 pairs. In this case, I'd need to add 4 more 0 pairs until I have a total of 7 positives, at which point I can take those 7 away, and I see that I'm left with a value of negative 4. This is a tricky concept, and it's going to take practice. But basically, when you have subtraction problems with integers, often you're going to need to add 0 pairs if you don't have the right number of pieces to remove. So be really careful to notice what kinds of pieces you're being asked to remove in each problem so that you can think carefully about if you have those or if you're going to need to add some zeros in order to complete the problem. All right, that's it in terms of tips for tomorrow. So I look forward to seeing you then and going through more about the chip model.